an LED power supply, 12 volts at 2 amps. I've been doing some testing this already because I just couldn't wait really. I wanted to see if it held up 12 volts under load, and it did actually. This is rated 2 amps. I put a 2 amp load in it and it held 12 volts. I put a 3 amp load in it, it held 12 volts as well, so that's a good start. But then I noticed there was a wee flash in the back when I turned the power on. So I did some high voltage tests and I discovered what I think may be an issue with this screw at the back here actually going in too far. So I've done some tests and I'm not sure if I've maybe weakened it, so this may go bang. It's not gone bang. That's a good start. It's still working. It did, however, fail the high voltage tests. Let me describe the tests I did. Now notice that I'm using the American power colours here simply because that's the only colours I had. I didn't have brown, blue and the green, so I used black and white and green. And in America, I believe black is live and white is neutral. Yeah, quite interesting that, because in our old colour code in the UK, it used to be red is live and black is neutral. And I remember you used to get the American video games, like Atari games used to come in and they used to be all wired wrong because people thought the black was the neutral when they wired them. And pinball machines, all the American stuff ended up wired wrong in the UK. So let's get this cheap LED tape out the way that's quite good for testing. And let's open this up. So this case, this unit came from, I should have actually looked that up. I'll look that up later. It came from a UK supplier. I had its box here. And it was called Lead_Son, S-O-N-E. But let's open this up. So a screw comes off the back. The dubious screw. Is the end of that slightly? Yes, it is. The end of the screw is black. It has arced. So let's get up close with this and see what we've got here. We've got a that's where it's been hitting. It's been touching the side of this. All right, that's an 8-pin chip under there, the switch mode chip, I'm guessing. And it's actually been touching the end of the heatsink. Let's put that screw in and see what that's like. Oh yeah, that screw is just way too long. Oh, that goes right up to the metal and touches it. That's ridiculous. Even with that's quite thin, it's not really going to stop it from going in too far. That's not very good, is it? How does this come out now? We've got a screw here. So the tests I have already done, high voltage tests. First I connected live and neutral, I bridged them together. I'm quite liking the earth connection here. The earth connection onto the case is onto this punched hole here. I was looking at that one there. That's one of the fixing holes. So it's onto this raised surface here. And it's got a fairly big pit of the solder here. Although having said that, that just goes on to a sort of anodized surface. Is that conductive? Let's bring the meter in and do a simple continuity test. Yeah, it's not bad. It's a bit scratchy. It's got a sort of a coating on it that could actually be interfering with that. Yeah, okay. I suppose ultimately if a fault did occur, it would make good continuity suddenly because the mains voltage appearing over such a small area would arc probably. That's not a very good excuse, is it? Let's zoom out a tiny little bit here just so I don't give you nausea, overexposure just by like ramming it right up to you. So what have we got here? We've got the live and neutral coming in. Live is going through a fuse. That is the live, isn't it? Yes, it is. That's nice. It's going through a fuse, going to a discrete bridge rectifier here. The output of that goes to the smoothing capacitor, so there's no filtering. Oh, there is a class Y capacitor. Going from the bridge rectifier negative across to the negative. So it's negative to negative on both sides. Now, I did the high voltage test from the input to the output in this. I did right up to 2000 volts. And the only leakage must have been through that capacitor. I was only getting about 0.5 milliamp leakage in the AC test. That's actually fine. It has passed its input to output test. It's worth mentioning when you're testing from input to output, you have to bridge the positive and the negative together and the live and neutral together. The reason for that is because if you just connect at one of the terminals, you're going to stress all the components in the vicinity. You know, these rectifiers are going to see 2000 volts or something like that. So you have to bridge them together so they're pretty much bonded to the same potential in the circuitry, and then it will find the easiest route through the winding. In this case, it would be the positive here. Where is the winding of the transformer? It would be the positives here, goes straight to one of the windings of the transformer. So then it would find its way, it would actually be looking for a path from there through the transformer to the other side. And because they're bonded together in the output again, the easiest path would be the one connection that is connected straight to the output. It's not going through the diode. So what have we got in the back here? If this is the primary winding of the, you know what, tell you what, I'm going to blow this up. I'm going to get some pictures of this, and I'm going to see if I can find the data sheet of that chip. It's covered, unfortunately, with this sort of crushed heatsink. A heatsink that looks as though it's been designed to be folded up, but they've just mushed it down. So give me a moment, and I'm just going to see what I can find. Back again with proper pictures so we can actually take a closer look at them. So what we've got here is the mains is coming in, and it's going through the fuse, which is under here. Fuse. And it's going through the bridge rectifier, and then there's a capacitor at the other side, and the negative, this end of the rectifier is negative, this is positive, and then it's sort of looping underneath and coming up to the other end, so that's negative as well. I'm saying that, I should check. Yes, it is. I can see the band there in the capacitor, and it's marked negative. The capacitor is just connected across there. It's a fairly big 22 microfarad, 22 microfarad, 400 volt. Is it 400 volts? Yes, it is. So that's providing the main supply. The positive is going straight to one end of the primary winding. There is only one primary winding. The chip here is very interesting. All the pins are common together on one side, and these are all common together. These ones are going to the negative, so it's switching from these 4 pins to these 2 pins, and it's a very low pin count chip. And then the feedback and power appears to be generated more or less internally. I'm guessing that this is the power chip, and this is the feedback chip. No, I'm wrong. This is the power chip and this is feedback, because there's another capacitor. Everything's flipped here. So there's another capacitor which is dealing with the, that's negative, that's positive. It's dealing with the power supply for the chip. But it seems to be derived internally in the chip. And the reason it's going across here is just to feed positive supply to one end of the opto-isolator. So the chip is deriving a power supply internally, and I've worked out what chip it is. Then this is the heat sink, and this is the bit that was shorting out. So effectively the negative rail of the power supply was shorting onto the case. But it was very close. It wasn't quite there. It was just when it was powered up, it would flash over. I'm surprised that didn't trip the RCD. It must have just been such a really super brief spark that it didn't do that. The feedback circuit is super simple. So there's the primary side of the transformer, and here's the secondary side, which is fundamentally just going across there. They've got 2 pins here, I'm guessing, for this connection. I'm guessing that's just to polarize the transformer so it can't be put in the wrong way round, because they are more or less matched with the outline of the transformer here, so you could put it in the wrong way round. That is just a keying pin then. The output comes out and then goes through a big fat diode. I wonder what temperature that diode will get. It is a fairly beefy diode in here. So it goes through. There are 2 electrolytic capacitors. The reason they've used 2 is purely, well, it's 2 things. It means a low profile. They take up less height and space, and also it may result in a lower overall impedance, may be able to deal with the sort of higher frequencies better. So that'll be the positive side of the capacitors, and that'll be the negative side. Negative side is going straight out to the negative pin, and the positive side is then just going straight, nope, filtering the output. There's the LED and its resistor, so that's what is it, 5 101, 500, oh, 5.1K, that's quite high. So it's just going to run that little green LED at very low current. The feedback is through these components here. And what we've got here, I'm trying to remember what the number of that chip is. I shall look at it through a magnifying glass. It's a super typical chip. It's a 431. Now, sometimes it's got other names, TLP 431. 431 is an abbreviation. Let's just write 431 below it. What it is, it's a threshold detector chip when it detects a voltage threshold. So to do that, you set a potential difference with a set of two resistors here. And they've got extra positions here, so they can put extra resistors in just to fine-tune that. But basically speaking, you set the voltage by a potential divider based on two resistors that when the voltage reaches a 12 volts, it then the voltage on this chip will be its threshold voltage. And there's a small capacitor there to even that out, to avoid noise from the output, triggering that irregularly. When that happens, it turns on, and it basically pulls this pin of the optoisolator to the negative rail, and the positive pin is already connected to the positive rail via a 470 ohm resistor. So what happens is when it reaches 12 volts, this chip turns on, the LED in the optoisolator turns on. Let's draw the LED. And shines across inside the optoisolator onto the detector surface. And that then signals back to that feedback pin. This also got a capacitor here. So the positive is connected to the chip's power supply. It's going through that little sensor, then it's going back to the feedback pin with this capacitor just to remove any sort of glitches and transients that could result in instability. The circuit board does, the cover of this does say adjust, in the sense that it might have had a little adjustment pot, but they haven't included that here. If they had, all it would have done is add another resistor, maybe across, a variable resistor across one of these with a capping resistor as well, just to allow you to fine-tune the voltage. It's very textbook, it's very simple. And all the magic is done by this chip here, the one that's got the screw rammed into its side. So initially I thought it was a Texas Instruments chip, but I was wrong. It was our classic Viper chip. Very, very clever little chip. Typical power capability for the model that I think it is about, well, they're saying 8 watts. 13 watts for Dippy, but that's why they've got a heatsink on it, to try and extend that up to this 20 watt region. The heatsink does a thermal paste, but they've kind of pressed this down onto the top of it and then soldered it in. You wonder how good the contact in there is, because that's relying on, well, there's nothing pushing it on, it really is just soldered on just across that. Not sure that would go. The chip does have thermal detection, over temperature detection, and when it does, if it overheats, the output will turn off. So let's see. The drain and source, there's the two biggie pins. There's the really important ones. The drain is what's actually going to the transformer, and the source is what's going to the supply. It's got the VDD, that's right, that's the VDD pin, that's its internal supply pin, and there it is. There's a circuitry that's generating that supply locally. And all it needs is that capacitor across the output from that pin to the negative rail to give the chip its own supply. That's quite clever. The feedback pin is very simply via a 1K resistor feeding into a op-amp here, that once it goes above, in this case, about 0.23 volts, it shuts the thing off, so it doesn't run. Once that LED in the optoisolator lights, it turns the switch mode power supply off. What a super simple circuit. There's no filtering. That's not really much a surprise. I also want to say that there's insulation in the back of this. They've got a piece of plastic acting as the insulation. I did a high voltage test. That's the one where I thought I'd really annoyed it, because I did the high voltage test between live and neutral and earth, and there was a hissing noise. I reckon the hissing noise was actually a corona occurring at the sharp solder edges here. I'm not sure what that was. Something was making a hissing noise. Given that it's AC, it might just have been coupling from through the plastic. But having said that, that test was a bit extreme to actually do a over 1,000 volt test from live and neutral to earth, because that would normally, in the electrical industry, the maximum you'd test is about 500 volts, and supposedly in the IT industry, it's supposed to be 250 volts as a maximum you test it, which is a bit pointless because at 250 volts, that's not representative of the peak mains voltage in the first place in the UK. So the other things that are notable here are the Snubber Network they've got across the back of the coil here, with a couple of resistors, the capacitor and the diode. And all they do is they take that spike. When this turns off, it takes that slight spike away, because when you turn an inductor like the primary of this transformer off, it would create that sort of spike. So overall, it's a functional little power supply. I've not really tried it long term to see how hot it gets. Maybe I should do that. Put it on full load and have the circuit board out in the open and see how hot the components get. You know what? I'm going to do that. So I've had this powered up for a while. What I've used to load it, I've used a big strip of, a full 5 meters of RGB tape, but just with the red and the blue chips connected. So it's drawing about 2.4-ish amps, which, to be fair, is a little bit naughty because it's only rated a 2 amp power supply. The hottest component by far. I may have to, let's turn the light off here and you can see let's take the exposure lock off. Let's see if you can see this. That's not helping much at all, is it? That's slightly swamping out. That's not helping much at all. Right, let's not do that then. It's very stylish. I like the lighting at the moment. Let's try it just like it is here, and I'll focus down onto. Oh, look at it swamping out now. I've just completely screwed up, haven't I? Let's try and lock it to a sensible level. I shall change the focus onto this, and we'll see if you can detect. Is that working? The diode in there is round about 93 degrees Celsius. It's pretty hot. The chip at the other end, I've put some Kapton tape on it. I won't poke this because it is live. I've put some Kapton tape to act as a sort of, it makes it a better target for the sensor. And to be honest, I'm not getting much heat off the heatsink at all. Off the side of the chip, I'm getting about 50 degrees Celsius, which is nothing. Off the transformer, it's negligible. It's about 52 as well. The whole thing is mainly running about 52 degrees Celsius, except for that diode, which is probably about 90 degrees above ambient, but that's with a slight overload. So once again, the diode is running pretty damn hot, as happens in a lot of these power supplies. Kind of prefer things to run cool, but ultimately, well, it is slightly overload in this instance, but the diodes are always going to get hot. I guess they're just designed to operate at those temperatures. So overall, it's okay. I just feel, it's not really what I'd call. No, the circuitry is not hot apart from that diode, which is by virtue of the fact it's rectifying the full, it's dropping a modest voltage to the output. You know what would be interesting? To measure the voltage that is being dropped across that. So let's flip this over and get the meter in and measure the voltage when this is turned on. Just making sure everything's all right before I plate myself. So what voltage is being dropped across that diode? Here's the meter. It's set to... let's set it to 2 volts. No, let's leave it up to the 20 volt. That's fine. So where's the diode? The diode is there. Let's gingerly poke that across it. That's not right. What the heck am I... Oh, you know what? I can't really easily measure that because it's half wave, of course. Oh, that's not so easy. No, that's not just like DC across the diodes. That's not that easy to test. It's seeing the full voltage across the capacitors when that diode is off. Oh, so that's that test screwed. What would have been the best way to test that? Not sure. I suppose, well, I can't really tell the wattage it's dissipating. I know it's certainly getting pretty toasty. And I know the current going through it, but that's about it. But that's the gist of it. So this is typical. It's one of a range of power supplies that came from that seller. This one was it just says LED power supply, fairly generic. Oh, model number. Model number S-25-12. Input 85 to 175 volt, 70 volt AC, or 200 to 240 volt AC. I'm not sure which model this one is. Ultimately, it's 240. I'm giving it anyway, so I guess it's a 200 to 240 volt model. And the niggle that I've got with it is the fact that that screw in the end of the case was touching this heatsink, and that was, it was just on the borderline, and that caused that to flash over slightly. So it seems a bit of a design flaw there. They've used a far too long screw. There's another thing. You can mount this onto a chassis with screws through the back. You'd have to be very careful that the screws you used only went in just literally a couple of millimeters, because any further and they could actually start piercing this plastic layer and go onto the back of the circuit board. Interesting little power supply. It's very neat what they can do with the Viper chip, that it pretty much just does everything with just a small smash of components. It's a very neat switch mode solution.